Now let's move on to discuss about metrics in recommender systems. So the standard approach in recommender systems is to use the root mean squared error when predicting the rating that someone will give or to an item, or use the accuracy in order to predict whether someone liked something or not, like a binary problem. However, most often it makes more sense to treat this as a ranking problem if we have this possibility, since if the user is seeing a list of results, then it makes sense that we try and measure the ranks of the items instead of just the raw scores. So there are different ways to different ranking metrics. Two of the most popular ones are adjusted recall and precision at n, and the normalized discounted cumulative gain. So let's see each one in turn. So precision and recalls in recommender systems are not really different to precision and recall in other settings. We assume that we have a data set and we know what items the user liked in the past. So if we have a binary classification problem, true, false, it's very easy to calculate the positives and the negatives and then get the precision and the recall rate. So the precision and recall at n is a metric that is borrowed from the field of information retrieval. So in information retrieval, sometimes we deal with a huge number of documents. Let's say you're Google, for example, and you can basically provide the user with an infinite number of search results. However, you know that the user only cares about the first page. So you can calculate your metrics only based on the results of the first page and not all of the documents that have been recommended. So in a similar fashion, in recommender systems, quite often, like a service like Amazon will have a huge number of products, but the users will only care about the few products which are on the top when they search for a particular type of product. So what we do here is we have a train and test split for each user, and we decide that there's some kind of cutoff point. Let's say we care only about the top 10 or top 20 items, and we'll calculate the precision for each user based on those top 10 or top 20 items. And then we average precision across users. So if an item is not in the top 10 or top 20, then we can consider this prediction as being negative. If this item should have been predicted as being in the top 10 or top 20 or whatever threshold is, but it wasn't there, then we consider this prediction a negative. The normalized discounted cumulative gain is another metric for ranking. So the idea is that you get a larger score for making correct predictions on more relevant items. So we'll see how relevancy is defined shortly. And the lower you go down a list, then the lower the relevancy score. So it's more important to get a correct prediction for the first 2, 3, 4 items on the top rather than for the items that are at the bottom of the list. And once again, we can also set a cutoff point. So we say we care only about the top 10 or top 20 items. So the traditional formula for DCG is the relevance over this discounting factor here, the logarithm of 2 of I plus 1, where this I is essentially the first item on the list and then P is the last item on the list. So as we go down the list, then the lower the gain is. However, there's a normalized version of it. We won't go too much into the details. The normalized version obviously provides values between 0 and 1, so it's more easy to understand. So let's see a worked example of how we would calculate discounted cumulative gain in this case. We won't use the normalized version because now we're just going through an example. The normalizer would essentially just convert the score we would get here in a value between 0 and 1. And in this example, we assume that we have a recommendation system, because obviously this metric can also be used in other systems, for example, in information retrieval. And the relevancy is defined by the rating that the user has given. So our recommender system has recommended 3 items from our test set, and we have the score that the user has given for each one of those items. So we know that the user in the test set rated item 1 as 8 out of 10, item 2 as 5 out of 10, and item 3 as 9 out of 10. So then we run the formula, and as you see that we have the scores here 0.8, 0.5, 0.9. However, these are discounted. So the first item gets a higher score after applying the discounting factor than the item 3. Even though item 3 has a higher score as rated by the user, item 1 in this formula gets a higher score. Why? Because it's the first item that was recommended. So ideally we'd like, for example, item 3 to move to position 1 or 2. Why? Because the user in the test set has rated this as an item that is worth 9 out of 10, and this would give us the highest score. So that's the main idea behind discounted cumulative gain. Essentially, we have a test set, the relevancy is equal to the score that the user has given to an item, and then we simply discount so that if we make a very good prediction, if we make a prediction about an item that the user loves, but it's in the bottom of the list, then this prediction will adjust only a very small amount of points to our final score. So this logarithm of base 2 discounting obviously can be, some kind of other logarithm, which essentially makes sure that as we go down the list, any prediction that the recommender makes adds only a score of 0, because a logarithm dividing by a logarithm will eventually make our scores go to 0. So that's it about discounted cumulative gain. It's a pretty simple but effective idea for ranking lists. And now let's move on to discuss about diversity and serendipity metrics. The diversity and serendipity metrics are there to solve the issue of making the recommender systems avoid to recommend the same items again and again. So this is something that can happen in practice quite often, especially in content-based filtering systems. So we want to avoid it, and there are some different heuristics we can follow. One is the intra-list similarity. So how dissimilar are the recommendations within the same list? So is, for example, the recommender suggesting 5 different DVD sets of Star Wars, or is it suggesting completely different movies? The coverage, the percentage of the user item space that is recommended. The serendipity is defined as the amount of surprise around the relevant recommendations. And finally, the novelty. How surprising are the recommendations in general? So for the intra-list similarity, we have the following formula, and here's an accompanied reference. We can just calculate the similarity between all the items in a list and just average them. Yeah. So this can help us identify whether on average the recommended products are very similar across most of the users, and then try to come up with mechanisms in order to fix this. In terms of the coverage, by coverage we can either have the item coverage or the user coverage, where essentially this describes the percentage of items over the total number of items, or the percentage of users over the total number of users for which we can have a recommendation. And we can combine this in order to get the catalog coverage, where it's the length of the catalog lambda over n times u, that is the total number of items and the total number of users times 100. So there will be situations where some items are not recommended, or we have many new users joining the platform for which we don't have data and we can't offer a recommendation. So the coverage helps us understand whether we are actually recommending most of our catalog to most of our users, or whether there are parts of our catalog or users which are unserviced essentially. So we would need to do something to fix this because we're missing a profit opportunity there. So now let's talk about the serendipity. In order to define serendipity, the first thing we need to do is to define the surprise equation. So the surprise equation simply describes the probability of an item being recommended. So this is calculated as follows. That's the total number of items n, and that's the rank of an item across all users. That is, how likely is it to be recommended if we don't know anything about the user. So we simply subtract from n the rank of the item, and then we divide by n minus 1. So this means that if we're talking about the most popular item on the list, then the probability of this being recommended would be something like 99%. Whereas if we're talking about the last item on the list, then the probability will be close to 0. So once we've defined the surprise equation, it's very easy to define the serendipity equation. We have to go across all items and take an average, as you see here. And we also have a relevancy term, so we might only take the top 20 or 30 items for a user. We assign, for example, the score of 1 to all the items in the top 10 and score of 0 to all the others. And the magic happens here. So we take the maximum of this expression and 0, just to make sure this expression does not go below 0. And we calculate the difference in the probability of an item being recommended for a user and the same item being recommended for all users. So the intuition behind this formula is that if there is an item that has a high probability of it being recommended to a user, and whereas this item is not popular in general for the rest of the users, then our algorithm is good in discovering those niches of products and users. Our recommender system, if it receives a high serendipity score, it means that it has actually figured out that, yes, this user, for example, is outside of the normal zone, what the average looks like, and yes, the recommender system is recommending good products for this user. So the serendipity has to be calculated for each user individually. And this leads us on to the novelty metric, where the novelty is simply defined as the sum over all the surprise equations of all items. We take the logarithm base 2 of those items over n. So this is basically a different way to measure the surprise over a user's recommendations, essentially. So we're using the logarithm here in order to avoid getting very, very high values for this metric.